A very pleasant good evening to you, wherever you are. My name is Brian White. I am from the JPL's Education and Communications Directorate. Welcome to the Von Karman Lecture Series. In 1783, the first crewed hot air balloon took flight in Paris. Crowds came from miles around to view the spectacle, including a few signatories of the Declaration of Independence. As the balloon lifted higher, a spectator asked the inventor and American founding father, Benjamin Franklin, what this new invention would be used for. Franklin replied, "What is the use of a newborn baby?" Days later, in a letter to a colleague in a more serious tone, he concluded that ballooning could pave the way to some discoveries in natural philosophy, which at present we have no conception. How right he was. Today, scientific ballooning is the last bastion of guerrilla science, providing well-tested, reliable, low-cost, moderate-risk platform that helps prepare the next generation of scientists, engineers, and instruments. Our first speaker tonight, Dr. Jose Siles, earned his MS and his PhD in electrical engineering at the Technical University of Madrid, Spain, is a Fulbright postdoctoral research award winner, has done study at the University of Tor Vergata in Rome, Italy, and at the Observatory of Paris in France. He was the LO Subsystem lead at the Stratospheric Terahertz Observatory and part of the Antarctic team deployed in 2015 and 2016 for the integration, test, and flight of this NASA balloon mission. He has spent a total of 5 months on the ice during those 2 campaigns, and currently he is a research engineer at JPL working on the next generation of sub-millimeter wave high spectral resolution cameras for astrophysics, planetary science, and earth science. Finally, he is an instrument-rated pilot and volunteers as president of the LA chapter of the Fulbright Association. Please welcome Dr. Siles. Have fun.
Thank you, everyone, for being here tonight. I'm Jose Siles. I'm a research engineer here at JPL. I've been working here for 8 years so far. Actually, a little bit more of 8 years and a half. But 5 months of that time, I spent it here on the ice, working on this crazy idea, which was taking a large telescope, put it on a giant balloon, take it all the way up to the stratosphere to look at the stars. So when these guys at the public office asked me to give this talk, I couldn't find a better way to do it than taking you with me on a journey to explore the universe from Antarctica to the stars. So I hope you are warm and comfortable. It's been a chilly week here in LA, not as cold as it was there when I was there. So I hope you like this. This is McMurdo Station, Antarctica. Just a few months before our team, the Stratospheric Terahertz Observatory team, STO2, arrived there to mount this telescope. And here's the nighttime. We didn't get to see this beautiful picture because it was daytime when we were there. But I want to point out a couple of things here. First of all, of course, this is the Milky Way. But what we see here is the past, actually. The Milky Way spans 180,000 light years across and 2,000 light years tall. But the most amazing thing here is that there are 100 to 400 billion stars in our galaxy. So you can at all imagine how many galaxies there are in the universe. And just try to extrapolate that to the number of stars, it will just blow your mind, the number. But it's obvious that with so many stars, the stars has to play an important role in how the universe evolves. Every scientific every scientific mission starts with a question, and we need to find answers to that question. And that's what STO2 wanted to do. So let's start with this molecular cloud. It's a lot of gas, particle, dust that at a certain point collapses because of gravitational attraction. And then all these particles start hitting each other, and the temperature raises from kelvins to millions of degrees Celsius. And because at the end it's a gas, the gas is going to tend to expand. So it has to be something that cools down that cloud to make that collapse continue in order to eventually form the star. So that happens with the 2 major coolants of the interstellar medium, ionized carbon and atomic oxygen. So STO2 will look at those emissions to try to trace these star-forming regions. Eventually, we form stars and then planets, and then the star will die as, for example, a supernova. And all that material is ejected back to the interstellar medium, and the cycle just gets back to the beginning. At every single point of this cycle, we have emissions in the far infrared or submeteor waves that give us information on what's going on. We cannot see this in the optical spectrum because the clouds are opaque at those wavelengths. At these frequencies, we can actually see through different clouds that are on your line of sight and see things that basically happen in all of them. These are the science goals of STO2. As I said, determine the life cycle of interstellar dust and provide templates for star formation. So coming back to this photo in the beginning, this is what we can see with our bare eye. It's a quiet universe, quiet sky. We see our galaxy in the center. It's beautiful, right? Not much going on. It looks like it. This is the visible. But if we look at other frequency ranges, things are different. Now, there are a lot of things that we cannot see with our bare eye that are going on. This is, for example, gamma rays. And this is the far infrared, the sub-millimeter wave spectrum. So now you can see here a lot of dust, clouds, nebulas that probably are forming stars. There are a lot of processes going on there. Let's actually zoom in one region here. This is Orion. This is a map of Orion at this sub-millimeter wave range. And you can see all these emissions, which are different molecules, which are actually life-enabling molecules. So studying the universe at these frequencies gives us an idea of where we're coming from and when we're going. In fact, NASA's COBE, this mission, found out that 50% of the luminosity and 90% of the photons emitted since the Big Bang are in the sub-millimeter range. So it's really important to study the universe in these frequency ranges. But how do we listen to the stars? Well, at the end, it's like a radio. So you have, this is a typical radio, the same that you will use to tune your favorite radio station, working at around 100 megahertz. So when we want to tune at carbon, oxygen, nitrogen, we do the same. It's pretty much the same concept, except that the frequency is like 10,000 times higher, which means that the circuits that you have to build this radio, actually now at this frequency, are so small that actually fit in a piece of your hair. They are micron size. So it's really challenging to design this technology to build a radio, which we call now radio telescope, to tune to carbon, nitrogen, or other molecules. So that's what we wanted to do. So 4 or 5 years ago, or 4 or 5 years before the mission started, we went to Antarctic actually, this is the concept. This is the concept of the mission. So we have a telescope. It was a 0.8 meter telescope. The signals, of course, are faint, so we need large apertures. You put everything. You have actually the receivers there on the back. You put everything in the gondola that will hold to the balloon. You have some electronics and computers here, some communications antennas, GPS, of course, elevations and azimuth control. Laura will talk more about that on her talk. And 4 years later, 4 or 5 years later, here we are. STO2 launched in Antarctica, December 2016. And now you have this beautiful concept as a reality. And this is a radio telescope, but I like to call it actually a time machine, because I said that when we're looking at the stars, we're looking at the past. So I don't know if it's really a radio telescope or a time machine. I think it's a time machine. Launch configuration. So we have a huge helium balloon, 40 million cubic feet, and around 140 meter diameter at float. You don't see it fully inflated here because it just actually gets fully inflated when it's at float altitude at 130,000 feet. There's a cable that connects with the payload that you see here, which is actually this. It's 22 feet tall, and the launch vehicle. And let's go flying. So they're going to release the balloon in a second. The balloon is going to line up there on top of the track. The track is going to back off and release the balloon without the payload, of course, crashing into the launch vehicle. I'll just see in a second.
There it goes, blowing away. Solo away.
There you go. So this actually is one of the most critical parts because we have to go all the way through the atmosphere, through all this thermal variation until we get up to the stratosphere. So you have to really design all these components very well so they take all that temperature variation during the climb.
Tower, do you copy? This is Tower. CSA rate. 1400. All right, great, thank you. All stations, safety range clear.
It's flying. It's not spinning.
This is how it would look like from the gondola, actually. Crazy, right? It's really impressive. That's Mount Erebus, a huge volcano on the background. And if you remember this from November, right, this is a very fancy looking control room that we have here at JPL, and you have all these guys very happy with the inside landing on Mars. So this was after landing, everyone concentrated here before. So Antarctica is pretty much the same, right? So this is Chris Walker, the principal investigator of the mission from the University of Arizona. Other colleagues, myself. After lunch, we were happy and concentrated here during the ascent, making sure that everything was working well. So again, balloon is just like doing science like in the old days, right? It's not as fancy as the flight missions, but it's really cool to be there. So one of the regions that we saw with this mission was the Carina Nebula. It's beautiful. It's one of the most active star-forming regions in our galaxy. And I'm going to let this here, and I will come back to this later. Let's go back on time a little bit. So this is not the first balloon mission, of course, the first scientific balloon. And none of the missions that you can find online is the first one. Actually, the first NASA balloon mission, or if one of the first, was this NASA Echo. It went all the way up to space. This balloon was inflated in space, 1,500 kilometers, and it was a communication relay, actually, and did some atmospheric measurements. But again, that's not either the first scientific mission. If we go back to 1912, Victor Hess took a ride on a balloon, went all the way up to 5.3 kilometers to measure variations on radiation. And because of this experiment, in 1936, he got the Nobel Prize in Physics for discovering the cosmic rays. So balloons give you amazing science. Since then, more than 10,000 missions and counting. In astrophysics, Earth, planetary science, most of them actually are in astrophysics. And I don't want to go through the list, but I want to point out that many of those are in the far infrared, gamma rays, X-rays, and there's a reason for that. And the reason is the atmosphere blocks the radiation at those frequency wavelengths. So you really need to go to space or go almost to space, which is, for example, why you want to go a balloon. You could go to an airplane as well, not in this frequency range, but in this. But again, it's not as clear as it is in space. For our specific project or mission, the submillimeter wave spectrum, this is how the coverage. Imagine your cell phone and going here to Atacama, but now your cell phone is trying to receive this ionized carbon and oxygen from stars. At 4.2 kilometers, where those carbon and oxygen emissions lines are, there's no coverage, so we cannot see anything. Well, let's go to an airplane. This is how the sky looks like with the NASA Sophia airplane. It's getting better, but still a lot of regions where you cannot really see much. So if we go with a balloon, things look much better. So that's one reason why we want to use balloons. But there are other reasons, like technology demonstrations, cost. We have seen that for our specific application, we don't really want to go with a ground telescope because we cannot see anything. But it's not cheap either. So the cost of ALMA, for example, is more than $1 billion. It's not cheap. We can go to space, but it's, of course, very expensive. You have to have a very reliable, very well-tested, reliable technology, very mature technology, very low risk. Things have to be tested and documented properly. So this mission, Herschel Space Telescope, was a some-millimeter wave mission, far infrared. It costed around $1 billion. We can go airborne with SOFIA. Again, for what we wanted to do, is not the best, but it gives you very good data. But it's not cheap either. It costs $100 million per year, more or less. But if we go with a balloon, now the cost is between $5 and $10 million. So that means that you can test new technologies, get that level of maturity, demonstrate those technologies in flight, and that way you can pave the future for future space missions. And then you can also land and recover the payload, do updates, and fly again. So it's actually a perfect way to do this technology demonstration at the same time that you get great science. But the technology that we use in balloons, it can be used for many other space missions in the future. As we are saying, it paves the way for future space missions. So for this specific technology that we were using in STO2, it can be used for water mapping in ocean walls. It could be used for water and thermal mapping in comets. It could be used for monitoring Earth's health. For example, this is an ozone map that was taken with a mission that is currently flying. And we can do atmospheric experiments as well, like a rain radar imaging or understand cloud humidity. So a lot of applications as well. OK, 4 years. We have all these crazy small circuits that we have to develop and put together. And we did it. This is in Texas when we put all this together the first time, and this is all the team. And I imagine that you build a 10,000 pieces puzzle. And I tell you, you need to take it apart and rebuild it in just a couple of hours. You will tell me, wow, you're crazy. We're not going to do that. Well, that's what we did. We took the telescope apart, put it in boxes, and sent it to Antarctica. So here we go. Everyone in the team gathers in LA. We fly from here to Sydney, Australia, a few hours there, then Christchurch, New Zealand. You have some training there, survival training. You get the cold weather gear there. And finally, you take a military, an Air Force aircraft to go to McMurdo Station in Antarctica. This is the beginning of my trip, and it's not that I thought that was very interesting for you, see my luggage. But what you see here is actually a subsystem of the radio telescope. It's very sensitive for electrostatic discharges. So we cannot just put it in a boat for 6 months and expect that it's working. We need to take it with us and make sure that it's transported in the correct way. And it's like doing science like in the old days, right? So I went across the wall with that. Actually, if you see there in the table, you can see it afterwards. The big piece there is one of the parts that were here that flew, and we recovered after and brought it back. This is myself wearing the cold weather gear before boarding the flight. And it's not that I wanted just to take the clothes, just to, put on those clothes to take a photo in front of the passenger terminal here for Facebook, which I really wanted, OK? It's because we need to board the airplane like that, just in case that something happens. Maybe you can survive on the ice for, I don't know, a couple of hours. So here we go. This is the airplane, the US Air Force airplane. And you fly like this stopped working. OK. So you fly like cargo. So you have all the food there, parts and everything, and all the scientists and all the personnel there are cargo. But believe it or not, it's more comfortable than a commercial flight. See how much room you have for your legs? OK, so another reason why we want to go to Antarctica. Well, this is one of the first photos I took from the airplane when we got there. And if you see here, it's beautiful, right? But there's nothing. So if your balloon fails and falls, the worst thing that can happen is you make a hole on the ice. Not a big deal. But the key point is that the Antarctic vortex keep this wind circulating around the continent. So when we launch the balloon goes around and around the continent. It doesn't go out, and then you can just, after your mission is complete, you can recover the payload. You can land back on the continent. Another problem, well, there's not really an airport, so here you have this huge airplane landing on the ice. It's the smoothest landing that I ever seen in an airplane. It was amazing. It's just really, really soft. McMurdo Station, as you see, looks like, I don't know, like an old scientific base, but really, really cool. The sea ice there. More interesting things. This is Robert Falcon Scott's hat that he built during his expedition to the South Pole. It's still there. Actually, you can go in there and you have even these food cans still there. It smells not really well, but it's very cool to feel like those old explorers. And that's what balloon is in the end, right? You just go there and try to put the giant balloon on a giant telescope on a balloon and feel like an explorer. It's really, really cool. The beach is frozen. They tell you that if there's a crack and you fall, you have 10 minutes to get out. I found a crack. I put my hand, don't tell anyone. I think that I wouldn't make it more than 1 minute. This is really, really cold. A galley, a fire station, a small hospital. Don't expect to get surgery there. If something happens, they need to medevac you. And there are not many flights, so you get really well tested before going there. And ice, a lot of ice. This is the most beautiful ice I ever seen in my life. It's just this turquoise blue. It's just beautiful. And some challenges. Well, this is Mount Erebus. This is the view from our office or our hangar where we were building the telescope. It's an active supervolcano. These actual fumes from the volcano. And it's very close. If these things get crazy, I don't think that we can run or ski fast enough. This is the hangar. We were not at McMurdo. We were like 40 minutes away from McMurdo. We have to take a transport every morning. This is the sea ice. And this is important because we have these very small devices that they are ESD sensitive. And there's no ground connection here. So you basically have to be very, very careful when you assemble the telescope back again because any discharge, and it's very dry there, so you have to be really careful and wear all these protections. Because if you discharge on your equipment, you kill it. Stormy days. It's the same photo as stormy days. In 2 or 3 minutes, you get white out. So you need to be careful when this happens because you don't pretend to be walking around when you don't see anything. You don't want to fall into a crevasse. That's not a good idea. And another important thing, again, we have to put together this 10,000 pieces puzzle in our case, 4 weeks. So don't forget anything. We have to take all the tools, all the parts that we might need if something goes wrong to fix whatever it goes wrong there on place. Because if something goes bad, you cannot call Amazon. You have to do it yourself. So you remember this from Apollo 13, the issue of the C2 filter when they have to make the round filters to fit in the square hole, and they have to do it with whatever they have in the spacecraft. So pretty much like that there. So whatever you have there is what you need to use. Inside the hangar, the scientists sitting there, and top floor, engineers working on the telescope here. A lot of parts, again, all these puzzles have to come back together in 4 weeks. The receiver, the 0.8 meter telescope that you see here, the solar panels, thousands of cables here. You really need to get inside and connect cables. Software, telemetry to control the gondola and the instrument on flight, the parachute for the landing. And at some point, again, within we made it happen, and that was back together, one piece, working. But we have a last problem, which is like, you have a telescope, right? So what do you need to test a telescope? You need stars or planets, right? But it's daylight. So how do we find, or how do we really point to stars? And also we have that we cannot receive the signal that we want to see from the ground, right? Okay, well, if you don't have a star, do it yourself. So what we did is to create a transmitter that you can see here in front of the telescope, transmit a signal that somehow reproduce the signal that we will see from a star, transmit it here to this reflector, which was on top of a container far away, and point the telescope to that fake star and do all the calibration, focusing, pointing, adjustment that we needed. Of course, at the end, you have to make sure that you're actually looking at your fake star. So you have to go there and cover the reflector and make sure the signal goes away. Please don't do this with a real star. You'll get burned. Okay, I said 4 years in 4 weeks, but in 90 seconds, this is how it looks like. So what you're seeing is the telescope just fall on top of the receiver, and now it mounts in the gondola. They're going to put on the bottom the computers and communication systems, and then we're going to start assembling the solar panels. And when all that is done, take it outside and do all these communication tests and transmission tests to make sure that the instrument doesn't interfere with the communications and all that, and of course that everything is working. After that, you are ready to fly. You bring it back inside and you just wait until there's a day where the weather is good, the winds are good to go for launch. So here you see we're doing some communication tests, back inside. Everyone happy, getting ready for launch. As you see, everyone was so excited and doing things very fast. It was not that fast, though. They put the landing pads on the bottom and just waiting for the winds to calm down. And you go to the launch pad, which is very fancy, and it's just ice. And here we go again. The previous one was real time. This is not, obviously. And everyone was really, really happy. Teamwork, teamwork, teamwork. So you cannot really build this or rebuild this in 4 weeks if you don't really work well alone. I wouldn't call them colleagues. I think they are really, really good friends. We spend so much time together that we got really, really close. You have to do this very fast. As I said, it's different to a space mission where you have much more time. You do this relatively fast, so you really need to trust each other. All these guys are amazing in what they do, and you have to really trust each other, work well together. You're there on the ice 24 hours a day together, and you really need to work well. Also, balloons, and Laura will talk more about that, is a great way to bring students, young scientists, to basically bring them to the process of building a whole mission from end to end and train them for future space missions. A lot of universities and other centers working together. So again, you cannot really do this alone. There's a lot of people working on this, and a lot of them that are not in the photo. So STO2 flew for 21 days. It went around the continent twice, and when the mission was completed, well, we just landed. So this is not from our mission, but this is how it looks like. So, you know, the balloon is turned, and then the parachute deploys. You now start falling. This is from outside view. You can see how massive the balloon is compared to the payload that is there. It's really, really impressive. This is how it looks like from, so it's really space. It's pretty much space. You can see how high we're flying, 130,000 feet. And you can land back on the ice. And I know that you were wondering if we do something else other than work in Antarctica. Well, this is New Year's Eve in Antarctica, Ice Talk, Antarctic Music Festival. We actually have, I think, like 20 bands playing that day. And it happened, it was a coincidence that we ended our mission just in New Year's. So, you know, it was not for us, but, you know, we can say that they organized a party for the team. It was really cool. By the way, midnight, they light all the time. So it's very, very cool to be on New Year's, actually, and just daylight all the time. A few weeks later, I think it was 2 weeks, we recovered the payload. This is how it looked like. So you see the solar panels are, of course, broken, but the solar panels are cheap. You can just buy new ones and put them back together. The gondola was intact. This is the falls picked that up. And this is how it looks like in the hangar, back in the hangar. So again, it just looks like new. Everything was working. This part was one of the subsystems that I took with me. You can have a look afterwards. It's still working. We recovered from the ice. We brought it back. It's still working. And the other one there is the new generation that we're trying to fly next. Because that's the advantage of the balloon. We can now update with new technology, with the next generation of technology, and fly again and try new things. Actually, because of the success of STO2, there's another mission called GASTO that will fly in 2021. And we're working on other concepts to fly larger telescopes, more broadband coverage to tune to different frequency lines. So this just, again, paves the way for future missions. But yeah, we're ready for another flight, yes. But I think after all that time in the ice, I think the team deserves a break. But the mission is not accomplished unless you don't get science. And this is the science we got from STO2. You can see here raw data. Those spikes are carbon that we saw. I showed you this photo before, and if you see an optical image of that region there's nothing here. With STO2, we saw carbon emission there. So STO2 actually found out how young massive stars impact the surrounding cloud. And that maybe regulate how the star forming process works. So really good science. Again, it will be more in future flights, but we got amazing science with this low budget balloon mission. So I want to conclude with this paragraph that I wrote on December 15 from McMurdo Station, Antarctica. So today, we got the first detection of carbon emitted by nearby Eta Carina 7,500 years ago. That's the time the signal takes to get to Earth from the Carina constellation. Carbon is basic to life, and these carbon emissions we are seeing today might turn into life in several million years from now. Likewise, ourselves, our carbon was probably part of a distant star-forming region millions of years ago. So today, as we look at the stars from the most remote part of our planet, using a large telescope on a giant balloon, we dig into our past to try to understand our future. Thank you.
Thank you, Jose. Now our second speaker, Dr. Laura Jones-Wilson, earned her BS in aerospace engineering at Virginia Tech in 2007, went on to study at Cornell University where she obtained her MS and PhD in aerospace engineering, specializing in dynamics and controls of space systems. She joined JPL in 2012 as a guidance engineer for Stable, a balloon-based pointing technology demonstration mission. Currently, she is a systems engineer on Europa Clipper, responsible for ensuring the solar arrays accommodate the radar instrument. Please welcome Dr. Jones-Wilson.
Hi, thanks for coming out tonight. I'm really excited to be here. So I'm Laura, and I am going to be talking to you about how the kind of other side, the dark arts of the ballooning missions, which are the engineering side, and how it's really a crucible for not only the science, as Jose was talking about, but also the technology and the teaming. So Jose went and gave a really good introduction about all the different science you can do on here, and some really cool aspects of it. So as he mentioned, one of the reasons balloons are so interesting as a platform is because they offer a lot of advantages over other opportunities for science. So for example, from a ground-based mission, you can actually have more tailored hardware. You can pick your own particular instrument or mission and fly that instead of maybe what's available on the ground already. You also get really clear seeing. You get lower wind speeds and larger coherence lengths higher up. And you can actually access different spectral bands. So Jose was talking about all the different ones that get blocked by the atmosphere. In order to be able to see those, you really have to go above the atmosphere, and balloons give you that opportunity. Another thing you can do, as compared to orbital systems, for example, it's a much lower cost. So obviously, Jose was talking about how that's more frequent. You can actually put up some more opportunities with your instrument, and you get to recover your hardware, which isn't usually what you get to do with spacecraft, and you can maybe even upgrade it and fly it again or over and over and get science in increasing quantities as you go through the different life cycles. So all the different science, we talked a little bit about astronomy and the astronomy that you can do from there. There's a lot of really cool things you can see. Black holes, dark matter, cosmic rays, even exoplanets. There's also some proposed explorations out there that are really cool. Some of the work that there's being done right here at JPL is studying ways of measuring quakes on Venus from balloons that you put around on Venus itself. So you don't have to sit on the ground at 800 Fahrenheit and try to take the measurements. You can actually try to make those measurements from higher up and get the measurements that way. On Earth, we can actually do climate measurements, magnetic fields, stratospheric chemistry, winds, all of these other great things we can learn by actually being in that wind column or that air column there. And then solar science, we can actually study how the solar winds come out from the sun and interact with magnetic fields here at Earth, and all the different cool interactions you might get with that. So as an engineer, though, this all science is great, but what I hear as an engineer is there's technology to be had here. This has needs for different parts of what engineers can do. So what can technology do on balloons? There's a couple of different things. So for example, you can develop technology for other worlds. And so if you're going to, for example, do that remote sensing technique where you're listening to the airwaves and trying to understand what the quakes are doing on the seismic activity, you can do that on a balloon platform here. And if you're going to send it to Venus, you're going to try it here on Earth first. So that's a technology we can start developing on balloons. Another thing you can do is develop new concepts for sensing. So I know that a lot of the new missions that Jose pointed out are actually trying out different detection types and different detectors, qualifying them, the technology on a balloon first, and then making the case that it's got really good science and maybe you should go on a space mission. You can also test in the upper atmosphere of Earth as an analog for other planets. So for example, if you wanted to test different sensors that are bound for Mars, you want to make sure that the atmosphere you're testing in is similar to Mars. One of the ways to do that is to go into our upper atmosphere where it's very thin and less dense and use it as a Martian analog. So Astra was actually a mission done here at JPL that was testing some of those, like an anemometer, a wind speed measurement, for Mars in our atmosphere. So these are all great platforms, but the really exciting thing for me is being able to build the balloon technology itself to be able to enable all of these missions. If you're going to be able to do any of these other cool things, you need a good balloon platform. And that's really where the mission that I worked on comes in. So I was on a mission called Bit Stable, and it was really about advancing the pointing capability of these platforms. So let's talk about Bit Stable. So Bit, these are maybe a little tortured acronyms, but BIT was the balloon-borne imaging test bed. Engineers are maybe known for being bad about that. But the balloon-borne imaging test bed was done by the University of Toronto, and they were building the gondola part of our balloon. So the idea is that you attach your balloon up here off of a tether, and this gondola is what held the stable portion. And so stable, Subarcsecond telescope and balloon experiment, was done here at JPL with a contribution of the camera by one of the folks in the UK. And so Bit Stable, the whole mission overall, was a technology demonstration mission with the intent of proving that we can get really stable pointing platforms off balloons. So the main objectives, and here's where I get into my engineerese, is to demonstrate 100 milliarcsecond pointing stability over at least 60 seconds, 1 sigma per axis, given a certain core stage pointing to within 2 arcseconds over 120 seconds. So what does that actually mean? If you're sitting on a really bouncy car and you're trying to take a picture out the window, you're going to get blurry images, right? Like, so the problem here is that if your pointing platform is shaking all over the place and you're trying to take a picture of something extremely far away and maybe even very dim or small, you're going to get blurry images and maybe not even see it. So what 100 milliarcseconds actually means is if you were sitting on Earth and were looking at the moon, so that distance, you'd be able to point your telescope such that it didn't vary by more than 2 Statue of Liberties standing on the moon. So it's really tight pointing. This was an order of magnitude or so better than some of the capabilities out there. So it was one of those things that we were really trying to do to prove that this telescope could really actually achieve this really tight pointing from a balloon. So we also had a couple other objectives. We were using a point source of light, and this is because we didn't want to use Jupiter, because if all you can use is Jupiter, it's nice and fat and got a lot of light coming off of it, then the only thing you can do with your science instrument is stare at Jupiter, and maybe you want to see at other things. And so we wanted to use a point source of light in the visible spectrum, because as Jose showed you, if you look at the universe in the visible spectrum, there's a lot of really cool points of light all over the map. And so you can look at any part of the sky and probably find a star that'll work for you, as opposed to, say, the infrared or something like that. We also had a signal-noise ratio, which is basically identifying how dim we wanted to be able to see the star. So we wanted to be able to look at relatively dim stars because they're more common in the sky. If you can only look at, again, really bright stars, you have to look at that one part of the sky. But if you can prove that it's a pretty dim star and you can look at any part of the sky, it gives you a better opportunity to do things like surveys or maps. And we wanted to do it on a balloon above 25 kilometers, because that's where the technology is really going to make the difference for the scientists. Okay, so why is that hard? The first is really thermal and dynamic disturbances. So when you start having a balloon that's going up to all of these different elevations, we actually had an 80°C difference between our hot case and our cold case, and making sure that our telescope would be nice and happy and give us a beautiful spot onto our detector of the star that we were imaging in all of these different cases was a very big deal. So we spent a lot of time figuring out how to focus the system and how to manage all of these thermal unknowns that we weren't going to know until we got down to the ice and we're trying it out. So we needed a system that was pretty impervious to thermal disturbances. But the real doozy is the dynamic one. So the problem with dynamic disturbances is, especially when you go up on a balloon, you're going to have motors and other things that need to actuate because you're trying to move your telescope to point at different parts of the sky. Those things you bring with you actually cause a lot of disturbances, especially high-frequency ones. And so, your motor, just like in your phone, things kind of buzz and vibrate. Those are disturbances from the environments, and those motors and reaction wheels can really mess up a pointing system if you don't take care of it. So what we did on stable is we developed what we call a power spectral density function that told us what we needed to reject. And you can see over frequency, we said there's these little spikes of things that we know are going to be on our system and might cause more energy going into our telescope than we really like. So the idea here is that we knew that this is what we were trying to reject, and we built a control system to say at each of these frequencies be able to knock it down so that we had a really clear, stable platform for taking pictures. All right, so let me show you a little bit about how we were going to do this. As a technology demonstration, we were only going to do this for one day. The idea was get up there, show we can do it over one night, and once that's done, we can actually do a really long-term science mission like the one in the Antarctic that would allow you to do longer-term observations. This was just a tech demo. So the tech demo was that we'd take off, we'd go to float around 35 kilometers, and just for reference, that's between commercial airliners and Aurora, so kind of in that range. We'd achieve our float. We'd be around 35 kilometers for the 8 hours overnight. We'd do our observations on various stars, and then at the end of the night, we would release, and we would land and recover. So that was the idea, and let me show you the hardware that we had built to do it. So like I mentioned before, this is the tether to the telescope, and this is the gondola. And the things that move the gondola are, there's one up here. So this is actually a motor that allows you to pivot, so you can kind of unwind the string. You can imagine that if you're trying to take pictures, being on a Disney teacup ride is not the most exciting part to take pictures off of. So you have this thing here to unwind the tether. You also have this down here. It's basically a reaction wheel and uses conservation momentum. So when it spins up one way, you spin your gondola the other way. And this allows you to move in azimuth and actually see different parts of the sky. And then if you peel back that gondola, you can actually see here, so this is our telescope, and right here is where we actually grab for elevation. So this part here has a motor on it, and it was an elevation motor, so we can kind of tip ourselves up and down and actually see different parts of the sky that way. So if you peel that back and you just get the stable part, stable here looks like this. To give you some sense of perspective, this is about, I did a bad thing. So this is about as big as I am. It's about as tall as I am. It's a 0.6 meter telescope. And what happens is the light comes in here. So we're looking at a star, for example. It hits our primary mirror. It goes into this part here, which is our secondary mirror. And there's this kind of baffle here. So it goes into that hole. And it gets picked up by this fold mirror on the back, gets reflected to our tip tilt mirror. I'll show you that in a second, and onto the camera. And so the camera is what actually takes the images, and we use that to centroid and say, oh, if our spot is drifting off of a pixel too much, then we need to correct for it. And so we'll tip a mirror to tip it back onto the pixels we wanted. So kind of show you, we broke it up into two parts. So the telescope part was the front end of the optical part, and the optical bench assembly was on the back. So again, the telescope was primary point of the telescope was to actually get the starlight onto the back end. And the back end here, the point was to actually get the light back into the camera and do the control system and the kind of brains of the operation to make sure that we were doing the control system properly. So the parts of Stable's technology that were really relevant actually lived here on the back, on the optical bench assembly. So this is the part that faces the telescope, and this is the part you can see from the back of it. And so the main parts of the control system, we had two computers. So there was a computer dedicated just to managing the data off of the camera itself. And that data that came off the camera was, again, we're really trying to centroid it. We're saying, OK, the spot is where on our detector, and where's the center of that spot? And so once we knew the center of that spot, we could kind of track how it was drifting over time and correct for it in our computer. So this is the brains of the operation. So our CNDH, our command and data handling assembly, actually made the decisions. It looked at all the sensor data, and then it actually sent commands out to our actuators to make sure that we corrected for it. And then here are our sensors. So this is an attitude rate sensor. It's like the gyro in your phone, except way better. The fine guidance camera here is from the University of Durham, and it's basically an optical camera that we characterized so that we could get the centroiding data. And then our actuators, we had a refocusing stage. So this basically moved the camera back and forth along the optical path so we could actually focus across a bunch of different thermal conditions. And then we had a fast steering mirror, which basically has a little mirror on the end here, and it tips and tilts it at very fine and high frequency motions so that when the computer realized that we were drifting off too much, it would correct for it using this thing. Okay, so how do we know that it works? So we put all the technology together, we had this system, it was great. So we actually built it up in the lab. So this is actually here at the MEC lab in JPL. And here's our bench assembly. You're looking at the fold mirror here. And the way that we tested it in the passive system was we said, OK, we're going to give it a light source. So this is an optical bench. We put a light source here and shone it onto it like a fake star coming through our telescope. And then we just let the California seismic environment do its job and saw if we actually could reject our ambient. And so what happened is that it worked. We're like, OK, we can reject noise. Great. So we got that. And then we actually decided, let's see if we can make this a little harder for ourselves. And we put a little stinger up here. A stinger is basically just a poker. Think of like a three-year-old kind of just poking. So what we did here is we had, again, a light source and an optical table. But this time we actually poked it at specific frequencies. I showed you those little spikes in our PSD. We wanted to know, could we reject at the frequencies we were worried about? And so what we showed here is that it worked. I'm not going to go into all the detail because I don't have enough time, but there's a really cool paper you should definitely go read. It talks all about it. So that being said, this is in a lab environment. Everything's like ambient environment for temperature. We don't have to worry about all the excitement of putting things together in the Antarctic. So how do we know it's going to work when we actually get to float? So the way that we did that was we had an analytical analysis. We call this a stop analysis, which goes through each phase of the different parts of the system and makes sure that at the end we're going to get the right answer. So the way that works is that we had a thermal analysis first. So we basically went out and looked at all the different environments we might see when we're at float. We put them together, did some statistics on it, figured out what that would look like. And that actually told us, OK, how is this thing going to be? Our mirror's going to be at this temperature. Our system's going to have various temperatures across the gradients here. Once we had that, we passed it over to the structures guys. And the structure people took that and said, OK, if it shrinks by this much and it moves by this much, this is how everything's going to move relative to each other. Once you know that, you can pass it over to the optics guys who say, OK, now my mirrors are now spaced this way instead of this way. And they can actually tell you what the quality of that light spot is going to look like on your detector. Once you know what that quality of your light spot looks like, you hand it over to the controls people and say, hey, controls people, here's the spot you get. What is it going to do? So the controls folks also take all the disturbances from the environment, timing and frequencies, information about the computer and the control system timing, and they do some analysis to show what the answer is. And that gives us our predicted at-float pointing performance. So we did all this. Another really cool paper you should definitely go read. And so we actually found out that we, at our worst case scenario, got 94.5 milliarc seconds over 60 seconds. If you fell asleep, it's 100 milliarc seconds is what we were going for. So we actually were able to prove that even in the worst case, we were going to achieve the pointing that we expected, which is fantastic. We're like, hey, this technology is great. We're going to get great astronomy out of it. So unfortunately, we lost our flight opportunity. And so this is about as far off the ground as Stable got. So our beautiful telescope's under here. And it ended up in an Indiana Jones warehouse next to the Ark of the Covenant somewhere. So, so that's where our Stable is right now. That being said, that's not the end of the story. The cool thing about engineering is that you learn things even if you don't really go out and fly. So one of the things that we were able to do is that our partners up at University of Toronto kept pushing this technology. They went out and actually built a mission called SuperBit. And SuperBit went and took this absolutely beautiful picture of the Eagle Nebula. And this is about 600 milliarc seconds. If you can imagine doing like 6 times better, it even gets better from there. So we knew the technology worked, and our partners were able to go on and actually show it. It was able to make the job. The other thing that we got out of this was actually team training. So the Stable's legacy is that we were all actually, everyone in this picture was on the team, and every one of us had been out of school for less than 3 years. So this was actually built as a project at JPL to train us and help us understand all the intricacies of how teaming works and how engineering works at JPL. So you can see we got exposure to in mission in about 3 years. And so those 3 years at JPL is really small scale. You know, I'm on Europa Clipper now, which is decades long. So being able to see something like that in 3 years is really an exciting opportunity for teams and gives you a much higher dose of what it means to be an engineer in this kind of team. We also had a lot more opportunities to interface with hardware. So you can see we're all standing around our flight hardware here. Everyone got a chance to touch it. We all got a chance to get in there and see what it meant. You know, when we design something on the whiteboard, what does it mean when we actually have to plug it in? And so that was a really excellent opportunity for us. And because the risks were a lot lower on something that's only a $5 million mission instead of hundreds of millions of dollars, we had a chance to actually get in there and really try things out. And for me in particular, so here I am, I was the project systems engineer on this mission. And a project systems engineer is responsible for everything that no one else thought of and more. So for example, one of my tasks was to figure out if we had a treaty agreement with Canada to ensure that our balloon was not going to land on a World Heritage Site. Who knew? So all of these little things that have to get put together to make sure that the team works, it was a really excellent opportunity to see that. In fact, here's some pictures, again, of me. And here's the truth of the matter is that all the cool Antarctic pictures, you know, are in that 4-week time period. All of the years that led up to it are mostly in conference rooms like this, where you're drawing things on a board, and every engineer from different subsystems are all standing together, and the systems engineers on the board and is like, all right, guys, you got to tell me when this signal goes to here, who picks it up? You do? What happens next? And then we kind of draw it out, and it all comes together in, you know, a whiteboard or in a conference room. And the really cool thing about balloons is that you actually get to go then build it and see it and actually be the one to implement it. And so that's one of the real magics of these type of team is that, you know, I got to be here and here in the span of just 3 years. So 3 years later, where did this end up? So you know, Stable is still in a beautiful warehouse, but it really did have lasting benefits. So for me, for instance, I'm actually now on the Europa Clipper mission where I'm a systems engineer. And I'll tell you, this is the Europa Clipper project science group, and I'm one of a much bigger team now. And so being able to understand how all of these interfaces work together is a really big part of why I feel like I can actually be in a team this big and still be able to communicate across all these people. So it's a really excellent opportunity. And so now we're actually building a spacecraft that's going to go explore the habitability of one of the icy moons of Jupiter. And I mean, that's exciting. If that's not exciting, I don't know what excites you. So the thing that's really cool, though, is that it doesn't actually have to be at JPL. My first introduction to JPL was this mission, but it was also my first introduction to NASA was ballooning. So my very first internship in 2005 was at Wallops Flight Facility, where they actually have a large balloon program there. And so the balloon program office has this balloon making lab. And so my internship project, my very first internship at NASA, was designing and building these balloons in their lab and actually coming up with different ways to fold and pack it so that we could see inflation dynamics. So here I am with my design balloons. And I came up with some different packing techniques using parachute packing approaches. And we packed it into the back of a little rocket nose cone that we put on the back of this 1970s NASA pickup truck. And what happened is we actually flew down, or we drove down the road, and this parachute would pick up at the right speed, and it would actually pull this thing off the back. You can kind of see it landing here. The balloon would pop out, and we'd study the inflation dynamics as we were driving down the road and saw how different packing techniques affected the inflation time and things like that. So again, I mean, this is the really, you know, cut your teeth on engineering, dumpster diving, shopping at the Pocomoke City, Walmart for components kind of engineering that you don't really get a chance to see. It kind of harkens back to the early days of rocketry and whatnot, where everyone was just trying to figure it out. And so a lot of that still happens in ballooning, which makes it that kind of guerrilla atmosphere where everyone's just like, let's make it work, and you're all in it together. The cool thing about that was that they were actually studying, my intern project was studying this inflation dynamics because they wanted to put this on Mars. The idea is that if you had a parachute and you could decelerate it, drop a heat shield, and actually inflate with the atmosphere as you were coming down. And then the envelope itself could be painted in such a way that it would warm up the atmosphere that was trapped inside the balloon and kind of create like a hot air balloon that could go down and sample some things. So I took this for my intern presentation in 2005, and I was looking around on the balloon program website and found this image 10 years later. So they're still looking at constants like this. The really cool thing is that balloons, you know, are a great way to study what we do here on Earth, but we're looking at ways to explore this as a platform even further out. So if you look at it, I mean, it's got a lot of cool advantages. Now, if you were talking about balloons on Mars, well, if you have a rover, which is excellent, we love the rovers, but a balloon allows you to cover more horizontal distance. You can revisit locations over time. You get more diverse coverage of regions, perhaps, because you get a little bit, you don't have to worry about topography or wheels or something like that. And then compared to some of your orbiters, you can also get higher resolution. You're a little closer to the surface. And it's one of the only ways to actually get information along that vertical column. And so it's a really exciting way to add to our understanding of some of these planets. So balloon missions, to kind of summarize all of this talks that both Jose and I did, they're really valuable contributors to NASA's mission, both to pioneer the future in space exploration for scientific discovery. Whether we're doing them on Earth, Mars, Venus, Titan someday, it's a really valuable way of taking information, training teams, getting the technology, and getting the science out of it. And as I mentioned before, it's also really important for training us next generation of explorers. So with that, thank you so much.
There we go. We got there now. Thank you, folks, and wonderful job from our speakers here. We are going to open it up for questions now. Now, if you're here in the house, we do have a microphone right there in that center aisle. Go ahead and line up there. You can ask your questions. They will happily repeat the question so everybody can hear it. And if you're watching home online, please type those questions in, and we'll bring them up and try to get them on. So questions, please, take it away. There we go. Somebody's working their way up there.
Well, I noticed we didn't talk much about the materials. Are the balloons mylar? Is element hydrogen used? Is there a porosity factor? Do you need to regenerate if there's a porosity factor? That stuff. What do you got?
So actually, well, it's not the screen back there anymore. In one of the websites, you can actually have all there are different types of balloon that NASA has, depends on the duration and everything. You can have all the specific details, and they're online. You go and check.
Did you use hydrogen?
Helium.
Helium, okay.
Yeah.
And is there a porosity factor? Do the balloons leak?
I think it can leak a little bit, but they have it all figured out, so basically it maintains. For example, for our case, it has some ballast. So I did lose its pressure with the flight. You can maintain altitude dropping some ballast, but there are the balloons that are a different system that they can maintain altitude and go through day-night cycles that NASA is testing right now.
Right. So you used ballast rather than bringing more helium along to, yeah.
For that specific balloon we're using.
I'll also mention that when I was at Wallops, I was looking at some of the balloon materials labs there, and they were working on prototype materials for balloons for Venus, because obviously Venus is a very different environment, and you don't want to put a piece of plastic that's going to just disintegrate. So they were actually looking at a mylar laminate with Kevlar on it, I believe, as one of the envelope materials. So it's going to depend on where you go.
Interesting. Thank you.
I noticed that you did use helium. Now, I realize that it won't explode like hydrogen will, but hydrogen seems to have a lot of other advantages. What was the main advantage of using helium over hydrogen?
I don't know. Do you know that answer?
For instance, hydrogen gives you more lift, and I assume you can do things safely so it won't explode.
That I don't know. That probably you have again to go to the balloon program office, and probably they have a lot of information about how NASA. As we were working mostly in the payload, but NASA, the balloon office, works on the balloons and separate. They have all these different balloons, so I'm sure that all the information you can find it online on the.
Okay, thank you.
If I had to speculate, though, trying to get just his payload down to Antarctica was quite a multi-step journey with things on boats for a long time. So even if you can work with hydrogen when you're out there, the cost of having an accident of some kind is probably a lot higher. So you want to maybe manage that safety risk.
How do you control the flight? The elevation, the position, we saw it goes around. And related question, why do you bring it back? Do you have any communication? Why don't you keep it there forever?
You don't want it to drift out of continent. And I mean, if it falls in the water, that's fine, you lose the payload, but you want to recover the payload, especially on these flights. So you want to make sure that it doesn't go off continent. So you terminate the mission before it does happen. At some point, the Antarctic vortex is going to disappear and it will drift off continent. You know where it is because you have GPS antennas and all that. You are in constant communication through satellite with so you are operating the balloon on flight. You have, of course, the pointing system. You can control the elevation and the azimuth. And Laura probably can talk more about the pointing system. But yeah, you have full-time communications. Hey, there are a couple of redundant systems. So you're controlling the balloon all the time.
In terms of trajectory control, you can control your elevation by making sure you have the right amount of lifting gas compared to your weight. And you actually do find that you'll get diurnal variations. You kind of move around over night, for example. And the way they manage that is with ballast. And so if you know that you're about to drop down, you can drop some ballast to try to maintain some of that altitude. But you don't really control, for most typical balloons, your kind of XY coordinates as you go around. That's really dominated by the prevailing winds. Jose mentioned that you have a kill switch so that if it gets too far away, you can actually take it down before it goes, say, out into the ocean. Or our flight was supposed to happen up actually in Norway. So if it gets too close to Russian airspace, you want to take it down before they do. But yeah, so that's the way you really you have to watch it. You manage it with GPS, and it's more of a knowledge thing than a control thing. There are some proposal ideas out there about how to make it more of a shaped form, kind of a dirigible type thing, where you can actually manage its trajectory in XY as well. But those are a little bit more involved.
Just to make it clear, the balloon just floats. So you control the azimuth and the elevation, but you don't control the path. It just gets the ride with the wind.
Right.
And what's the maximum elevation? Or?
It depends on the weight of your payload. I think it's around 40 kilometers, around 140,000 feet, something like that. Again, is the heavier your payload is, the lower you go. I mean.
Hi, thank you both for a wonderful lecture. Jose, I wanted to ask you specifically about the component you have on the table and the difference, or what changes you made between that and the new gen.
So the one that we recovered, which is the big one, it has is one of the drivers of the receiver. So it has 4 channels. So basically, it's like we had 4 receivers, right? All tuned at the same emission, or in this case, was carbon. Ionized carbon. The other one, it was the next generation. So of course we were flying that, we're planning to fly that, but at the same time we're working on the next step. Better designs, better packaging. So that the small one that you see there is actually 16 receivers, or 16 transmitter in this case. It's a transmitter.
Is that multiplexing?
Say again?
Are you multiplexing?
No, it's just 16 transmitter, and the receiver part will have 16 receivers. But it consumes less power than the other one, which is 4. This one has 16. Of course, it's much, much smaller. We use lesson learned from the other one to implement the new one. So in the next, hopefully, balloon flight, we'll try to fly the new generation. It also allows us to, in the same form factor, add more channels, add more frequency coverage.
Thank you.
So we do have 2 questions we had a lot of questions from the internet, and they were great questions, but we have time for 2 of them. So I'm going to start with a question from YouTube, kind of on the design you were talking about with planetary. Could we launch a Mars mission with a balloon to be launched from the surface of Mars, rather than what we saw in the image before?
Yeah, I mean, there are a lot of concepts. I think that if you give an engineer a difficult problem, they'll find a way to make it work. As we've shown before. Yeah, the specific concept that I was studying as an intern was there are some advantages to using the atmosphere that you have rather than bringing it with you, and mostly you're a lot less prone to leaks. And so if you lose a little bit of helium that you brought with you, then that's kind of the end of it. But if you can heat up and kind of keep replenishing the atmosphere you have, then you might be able to stay up longer, was the idea. But there are definitely concepts for a lot of different things. I mean, and launching from the surface would be one of them.
Very cool. And the last one from Northern Astronomy. What is the most interesting thing you've discovered from all of this research?
From a science point of view. Well, personally, I would say that is being exposed to this end-to-end mission in such a short period of time compared to flight. It's like a summer, well, summer is it's a little bit longer than that, but it's just intensive training. So you get to do everything. You get to do design. You fabricate it. You have design. You put it on a telescope and make it work. And you are with all the team. And at the end, you know, everyone does what is needed to help. So everyone does a bit of everything. So you are with the scientists. So you get to learn the science, even if you're an engineer. The scientists understand better the engineers. So everyone is there. So also this teamwork spirit, getting to work with all these amazing people, learn from the best people in the world to build this kind of technology, and of course the best scientists in the world. I mean, it's something that is really, it's a once in a lifetime opportunity, especially being there in Antarctica. So it's just amazing.
Yeah, it's really all about the teaming. I think that the thing that I thought was most interesting is, as a systems engineer, you think smaller mission might have fewer functions or fewer things you do, but it's really, you have to do all of it. You just have less time and money to do it with. And so you have to have interfaces. You have to have risks spelled out. So you really have to do everything in a small mission. It's how you manage them is a little bit different. And so all the systems engineering functions are there. You just got to do it. And so it's interesting to me to see how that discipline really just, it's required even at these tiny scales all the way up to something like Clipper.
Well, thank you very much. That is, unfortunately, all the time that we have this evening. I want to give a big thank you to our speakers. And a thank you to all of you who joined us, whether it be here in person or watching from your home, wherever you are today. Please join us in March for the golden age of exoplanet exploration. Details can be found on our website, jpl.nasa.gov. Thank you for joining us, folks, and have a great night.